Here are several more examples of how to balance chemical equations. So we'll start here with, this is actually barium peroxide. And again, remember this triangle symbol, or this delta over the yields arrow, means that heat has to be applied for this reaction to occur. So when you heat barium peroxide, which is in solid form, you decomposes and you get barium oxide, which is also solid, and oxygen gas released as a byproduct. So in some cases, an equation might already be balanced. And if that's the case, then you don't have to adjust any of the coefficients. You just leave it as it is. But we'll find here when we count the elements on each side that this one is not. So we will need to do a little bit of work here. So we have one barium on this side and one barium atom on this side. So that's balanced. And then we have 2 oxygens from the reactants and 3 oxygens from the products. Okay, so that's not balanced. And again, you'll notice here, as usual, the problem is with the oxygen gas and then oxygen being part of another compound as well. The best thing to do in this case is to multiply this oxygen by 3/2. Again, that will give us 3 oxygens and 3 oxygens. But now the bariums are going to be unbalanced. So now the number of barium on the reactants side of the equation is now 3/2, which means that now we're out of balance here, and we would have to adjust this. So we could multiply this by 3/2 so that the bariums are equal, but then that's going to change the number of oxygen. Then we'll have to multiply this again, and we're just going to keep going in this vicious circle where we're not able to actually balance the equation. Okay, again, the reason this happens, or the situation where you will have this occur, if you find this happening to yourself, then you should probably stop and look at adjusting the coefficient on just one compound at a time rather than the whole entire side, because that's the issue we're having here. When I adjust this whole side's coefficients, then that throws things off on this side, and when I try to multiply everything over here by something, some coefficient, then I get my number of oxygens thrown off, and I can just keep going in that circle forever and never achieve balance. So if you find yourself running into that problem, again, it's usually going to be in these situations with oxygen, try just adjusting the coefficient on only one of the chemicals in the compound. So either this one or this one. Usually, in fact, it's going to be the oxygen gas that you need to adjust. So I want to think of it this way. How could I get this to be 2, not by multiplying everything by some coefficient for all the compounds and all of the oxygen involved, but is there something I could multiply just this single compound by that would then add to 2 oxygens on this side so that it matches what's over here? And if I multiply this by 1/2, that is in fact what's going to end up working out for me. So if I have half of 2 oxygens, that's 1 oxygen, and then I have 1 oxygen from here. So now the number of oxygens is 2. Okay, and so I actually have balance in this situation. But again, I need whole number coefficients. So this is a 1/2. So I need to multiply all of the coefficients by 2 in order to preserve the ratio, but then also eliminate this fractional number. So the balanced equation should be 2 barium peroxide. When you apply heat to that, it yields 2 barium oxide plus 1 molecule of diatomic oxygen, okay, or oxygen gas. Okay, and again, if don't feel like it's balanced or you're not sure, go ahead and go through again and count your elements on each side and verify that it's balanced. So 2 bariums, 4 oxygen, 2 oxygen here, 2 oxygen here, that's 4 oxygen. So this is indeed balanced. Okay, we have a similar example here of decomposition. So we have another peroxide. So again, the O2 sometimes is the peroxide ion when it's bonding to something else. So, but instead of barium, we are bonding to two hydrogens. So this is hydrogen peroxide, which is usually in liquid form. And when it decomposes, it breaks down into water and oxygen gas. Okay, sort of like here, you have an oxide, in fact, in a sense. But normally we don't call water that. Water is just water. And then oxygen gas being released as a byproduct of the decomposition. So we're going to run into the same problem here if we try to simply multiply all of the coefficients by some value to adjust. So we have 2 hydrogen and 2 oxygen, 2 hydrogen and 3 oxygen. And again, it's this even-odd imbalance between the oxygens, which usually is going to cause us problems. So since this is basically the same setup as here, with the exception that this ratio is 2 to 2 instead of 1 to 1, I'm going to try the same thing. Okay, I'm going to have half of an oxygen. That was smooth. So if I have half of an oxygen, that's 1, 2 oxygen. Now in the products, I didn't change the number of hydrogens. I didn't change anything on this side. So now I am balanced. But again, I have this problem. So I'll multiply everything by 2. So 2 hydrogen peroxide molecules break down to become 2 water molecules and 1 gaseous oxygen molecule. Okay, and this should make sense in this case. It's pretty easy to see how this would work. If I lose one of these oxygens from the breakdown of each of these, then I would be left with 2 H2Os. Okay, and then those 2 single oxygen atoms will bond to each other to form this single molecule of diatomic oxygen. Okay, again, if you haven't watched the elephant toothpaste video yet, I highly recommend it. It's a good example of the accelerated breakdown of hydrogen peroxide. In the next example, we have terms instead of actual chemical formulas. With the exception of glucose, I've given you the formula for glucose, C6H12O6, because you probably not have that memorized yet. Glucose is just sugar. Oxygen is, again, O2. Carbon dioxide is 2 oxygen per 1 carbon, so CO2. Although this is something you should have memorized by this point, because it's a very common chemical and it's always involved in combustion, okay, burning reactions. So when I combine carbon dioxide and water in some kind of special chemical process, for example, like in the cells of plants, so I get sugars in plants. Well, how does that happen? Plants take in carbon dioxide from the atmosphere and water from the ground usually, okay, or they might respire the water in through their leaves, but they get water and carbon dioxide in their cells and they combine those through a special chemical process to create sugars, okay, to create carbohydrates, which then are used for energy for the cell metabolism. So these are the chemical compositions of each compound here, but is this balanced? Unfortunately, it is not. So we have 1 carbon here, 3 oxygen, and 2 hydrogen from the reactants. And from the products, we have 6 carbon, 12 hydrogen, and 8 oxygen. Okay, so there's some imbalance here. Now I'm going to start here by simply trying to balance one element at a time. All right, so if I had 6 carbon here, then this would be balanced. So I'm going to go ahead and change the coefficient on the carbon dioxide to 6 and see where that gets me. Now I would have 12 oxygen here plus 1. So now I have 13 oxygen on the the reactant side. And nothing over here changed. So my carbon's balanced, my oxygen is not balanced, my hydrogen is not balanced. Again, I usually would recommend leaving oxygen till last in problems that have many elements like this. Hydrogen would be second to last. So we're gonna try to balance hydrogen first and see where that gets us. So I have 12 hydrogen, I need 12 over here. So if I multiply this by 6, which means I would need 6 water molecules here. So again, I recount. Now I have 12 hydrogen, but I added 6 more. I added 5 more water molecules. So this is going to change to now 18. And my carbon and my hydrogen are balanced, but my number of oxygens is not. So how can I get this to match with this? And I don't really, if I can avoid it, I don't really want to change these coefficients of 6, because those are giving me the right numbers of carbon and hydrogen over here. Okay, in the glucose molecule, I have 6 carbon and 12 hydrogen, which is what I want. So I want to, if I can, adjust something on this side so that it matches what's over here, so that I don't destroy that balance that I've already created. So the only thing that I really could adjust here without doing that is the number of oxygens. So is there a coefficient I could put on this that would change this number from 8 to 18? And in fact, there's 2 in each of these, so I need 10 more. That means I would need a 5 here. So if I do that, this will be 18, this will be 18, and everything should be balanced. So the balanced chemical equation for this reaction is 6 CO2 plus 6 H2O yields 1 glucose molecule and 5 oxygen molecules. Okay, and again, double check your numbers if you feel like you may have made a mistake at any point. All right, down here we have H2SO4, which is, you should be able to name this. I'll give you a second to think about it. So maybe pause the video and think for a moment. Think about what these chemicals are and what they should be named. And go ahead and try giving a shot at naming all of these, and when you unpause the video, I'll give the answer and we'll see how you did. So I recognize in this compound an oxyanion and a hydrogen, okay, or a couple of hydrogens out in front. That should tell me when I have these hydrogens out in front and then something pretty electronegative like an oxygen or an oxyanion like this, that this is an acid. Okay, so this is a ternary acid, and so is this compound, in fact. So these are 2 acids. We'll name them in a second, and these are, well, this is nitrite and sodium, so this is an ionic compound, and this is sulfate and sodium, so this is an ionic compound. So we have an acid and 1 ionic compound yielding a different acid and some other ionic compound here. This acid is coming from sulfate. So this is sulfuric acid. Okay, again, the ic ending indicates that the ion is 8. And then this is just the ion nitrite, NO2, and with sodium as the cation. So this is sodium nitrite. HNO2 is, so it's nitrite with hydrogen to form the acid. So the ite is not the ending ic, but the ite gives us the ending OUS. So this is nitrous acid. And this is sulfate and sodium, so this is sodium sulfate. Okay, so those are the names of these compounds, just to give you an idea of what types of compounds these actually are. So we have this salt basically being dissolved in acid and yielding a different kind of acid. So this is breaking down and it's forming a new acid and then a new ionic compound or a different salt of sodium sulfate. Okay, we'll cover about salts and acids more when we get to the chapter on acid-base chemistry, which is the next section we'll cover. So let's balance this thing. Okay, now that we know what these compounds are. So we've got 2 hydrogens, 1 sulfur, 4 oxygens from this and 2 from that, 6 oxygen, 1 sodium, I'm running out of room here a little bit, and 1 nitrogen. Hopefully you can still see all of this. Okay, and then on this side we have 1 hydrogen, 1 nitrogen, 2 sodium. Actually, let's change that. 2 sodium there. The 1 nitrogen was on the bottom. 6 oxygen and 1 sulfur. Okay, so this is actually, it's looking pretty close to being balanced. I have the correct number of sulfur atoms already. I have the correct number of oxygen atoms. I have the correct number of nitrogen atoms. I just need to basically double, one on each side, the sodium and the hydrogen. So if I look at the compounds here, I'm looking for the ones that contain the sodium and the hydrogen. All of the others are in the correct ratio. So I need twice as many sodium. So that means I have to put a 2 on this. But now that's going to change my number of nitrogen and the number of oxygen that I have. So 2 times 2 is 4, plus 4 is now 8. So that takes care of the sodium, but now it actually has created an imbalance in the oxygen. But let's go ahead and try to balance the hydrogen first. So I have 2 hydrogen on this side, I need 2 on this side. So I'm going to go ahead and put a 2 as my coefficient here on the nitrous acid, which changes my number of nitrogens now to 2, and increases my number of oxygens by another 2, so the 6 becomes 8. And in fact, now I should have balance. I have 2, 2, 1, 8, 2, 2, 2, 1, 8, and 2 of each element. So this is the balanced form of the reaction. Okay, sodium phosphate. Again, give yourself a little challenge here, give yourself a little test, pause the video for a second, try to come up with the formulas for all of these chemicals that are named here and write those down. Okay, so sodium phosphate, hopefully you remembered that phosphate is PO4 with a 3 negative charge. So that means I'm going to need, sodium is a +1 as an ion, so I'm going to need 3 of those to balance this out. So sodium phosphate is Na3PO4. Okay, and then I discard the ionic information. Chloride is just the chlorine ion. So chlorine in an ionized state. It's not chlorate. Don't confuse this with the oxyanion. So there's no oxygen here. This is just chlorine and calcium. Calcium is a +2. So I need 2 of these -1 chlorines for this to balance and for the oxidation numbers to add to 0. Sodium chloride, again, chloride is just chlorine. And you know this compound already. This is just salt, table salt. So NaCl. Calcium phosphate, again, phosphate is PO4. -3, but calcium is a +2. So if I crisscross that, I'm going to have Ca3PO4 2. Okay, so I know the composition of these chemicals. Now let's try to see if this is balanced. It's obviously not already. I have 3 sodium versus 1 sodium. And I have 1 phosphorus versus 2 phosphorus. Oops, excuse me, 1 phosphorus, 2 phosphorus. I have 4 oxygen versus 8 oxygen. 1 calcium versus 3 calcium. 2 chloride versus 1 chloride. So some of these need to change. If I have 3 sodium here, I need 3 sodium on this side. So we will go ahead and try this. Okay, now I have 3 sodium, but I also increased my number of chlorines by 2. So now I have 3 chlorines there. That gets the sodium to be balanced. Let's look at phosphorus next. 2 phosphorus versus 1 phosphorus, so I need twice as many here. So we're going to try putting a coefficient of 2 there. But that now changes my number of sodium to 6. And my number of oxygen from 4 here to 8. So now I have 8 oxygen on this side. So now my phosphorus is balanced, but my sodium is back to not being balanced. Let's try the calcium. So I have 1 versus 3. So let's change this. So now I have 3 calcium and 6 chloride. Versus here 3 calcium and 3 chloride. So I actually need this to double. So this is going to go from 3 to 6. Which makes now this go from 3 to 6. So now I have 6, 2, 2, 8, 8, 3, 3, 6, 6. So that looks like it should be balanced. But we're going to double check on this one because we did a lot of manipulations here, so we may have gone wrong somewhere. So we're going to recount everything. 2 times 3, 6 sodium. There aren't any other sodiums coming from any of the other compounds. 6 sodium. Okay, sodium's good. 2 phosphorus. 2 phosphorus. 8 oxygen. 8 oxygen. 3 calcium. 3 calcium. 6 chloride. 6 chloride. Okay, so we have the final form of our equation, which is balanced. All right, here we have a combustion reaction. Okay, butane, which is a gas, a flammable gas, which is used sometimes in canisters and things like propane or something along those lines. It's a similar type of compound. And butane has a lot of carbons, which are linked in a chain, and then have hydrogens bonded to them. And when you burn it in oxygen, so again, this is why we need the oxygen here, is to enable the burning to happen, the combustion to occur. And again, with combustion, you're almost always pretty much going to get at least these 2 compounds as products, carbon dioxide and water. We don't always think of water as being a byproduct of combustion or flame, but it's there. Okay, it's there in the hot water vapor. It's just in the form of steam, so we don't always see it. It's all mixed in with the smoke and everything that's rising from the flame, all those gases. So I need to count this out. I've got 4 carbon. Let's use the regular pen. Versus 4, 7, 10 hydrogen and 2 oxygen. And on this side, 1 carbon, 3 oxygen, and 2 hydrogen. Okay, again, I notice even odd with my number of oxygens. And again, this is involving a combustion reaction or a reaction of breaking something down, decomposition. So this is commonly where we run into this issue. So I'm going to, again, try adjusting this by adjusting the number of oxygen molecules that I have. So if I wanted to get 3 of them as a product, I need to change this somehow. Luckily, there are no oxygens in butane, so that doesn't throw off the calculations. So if I had 3 over 2 of these, then I would end with 3 on this side. Okay, so that's good. I still need to balance my carbon and my hydrogen though. Okay, and the hydrogen it looks like I need 5 times as much over here. So we're going to try putting a 5 as our coefficient on the H2O. That, however, is going to change our number of oxygens now to 7. Which means, and this is 3 over 2 is just 1.5, so I'm going to need to end up multiplying that as well to balance the oxygen out. Again, you're seeing it. I'm not following my rule here. You're seeing an example of why you really shouldn't balance oxygen until the end, because we tried to balance it and then we balanced something else, and then that threw off the number of oxygens. So now we're going to have to rebalance it again. Again, there's no guaranteed or set path that you have to follow when you're balancing these. If you can just sort of look at it and see what coefficients you need for things to balance, then I mean, that's great. That works too. You just have to be sure that at the end of the day, you have matching numbers of atoms on both the products and the reactants side of the equation. So I still need to worry about the carbon though. I've got 4 versus 1, so I'm going to need to adjust that, increase this by 4 times. But that again shifts the number of oxygens that I have. So now I have 8 and 5. So now I'm up to 13 oxygen on that side versus 3 over here. Or let's just go back to 2 because we're just going to need to work with this now. So I need 13 oxygen there. So I need to multiply this by 13 over 2, in fact. And that will give me 13 oxygens. Okay, and that multiplier does not change the balance of the carbon or the hydrogen at all. So this is good except for the fraction. So we're going to multiply everything by 2. So the final form of our reaction here, our equation should be 2 butane Okay, you'll sometimes see this. Instead of written out this way, this is more of an organic chemistry way of writing it. You'll see it just written as C4H10. Okay, so you could write it like that instead as well. Plus 13 oxygen molecules. So we need 13 oxygen molecules to burn 2 butane molecules. And so when you multiply the 4 carbon dioxide and the 5 water molecules by 2, you get 8 carbon dioxide and 10 H2O, and then your equation is balanced. Okay, last example. Calcium phosphate plus silicon dioxide plus C, so this is just carbon, okay, or this is actually what's going on here is this is a reaction of heating using coke, okay, which is basically coal in a sense, okay, or it's pure carbon. And again, you can see the heat being applied here, so we're burning these, or we're not, we're heating them using carbon as the sort of the fuel source, or a side reactant, if you will. And that produces calcium silicate and carbon monoxide and phosphorus, okay? Phosphorus in the form of P4. So phosphorus is one of these elements that will bond to itself in various quantities, and so you have different types of phosphorus, like white phosphorus or red phosphorus or black phosphorus. So let's see if this is balanced. We have 3 calcium, 2 phosphate, phosphorus. Yes, 2 phosphate, but 2 phosphorus is really what we're interested in. 8 oxygen from here and 2 from here. So we need 10 oxygen atoms on both sides. There's 1 silicon and 1 carbon for now. On this side, we have 1 calcium, 1 silicon, 4 oxygen. Let's put the silicon here so it lines up. 4 phosphorus and 1 carbon. Okay, so we have balance here and here, but nowhere else. So we'll start with the calcium. Okay, I went ahead and rewrote this problem because the other page was getting a little bit messy. So I want to back up a little bit and come back to the beginning of the balancing here. So I have 3 calcium on this side and only 1 calcium on this side. So I'm going to need to try maybe multiplying this by 3 or changing the coefficient to that. So that would give me 3 calcium now and 3 silicon. And this will be 9 oxygen plus 1 from there. So that's now 10. Okay, so the calcium's balanced, but I have 4 phosphorus here and only 2 on this side. So I will need to double my amount of phosphorus on the products, on the reactant side of the equation. So if I do that, that also doubles the number of calcium. So that becomes 6. And my oxygens on this side are going to be 8 times 2, 16 plus 2 from that. So that will be at 18 now. So I balanced the phosphorus, but I've just now thrown off the balance for what I did balance before, which was the calcium. So now I need to try to rebalance that. So I need twice as many here, which means this needs to become 6. So 6 calcium now, 6 silicon, and 18 oxygen plus 1. So calcium's balanced, phosphorus is balanced, oxygen is not balanced, but that's okay. We're going to save that for last in most cases. So now I have 6 silicon on this side, but only 1 on this side. So I need a 6 there. But that also changes my number of oxygens. So now I have 12 and 16, which is 28 versus 19 over here. And my carbon right now is balanced, but my oxygen is not. So there's nothing left for it at this point except to try to balance the oxygen. Now, if you try to do that by changing the number on this, remember that's going to throw off these other elements that you've already balanced. So you don't really want to change this here if you can avoid it. The 2 elements we haven't balanced or haven't done anything to really, are the oxygen and the carbon. So this is probably the element that I want to, or the compound that I want to work with, the carbon monoxide. So I need 9 more oxygen on this side to equal 28. So I have 1 here. If I get 9 more, that would give me 10. So we'll try changing that to 10 and see what happens. So that gives me now 28 oxygen on this side, 28 oxygen on that side. But now I have 10 carbon. Okay, so now the carbon balance is off, but that's okay. It's pretty easy to balance this because there's only carbon atoms here. There's no other, I'm not going to throw off any other balance of any other element by changing the coefficient on the carbon. So if I just change this to match the number of carbon on that side, this should work. So again, let's go through and we'll double check. So I get 2, 6, 10, 6, 10, and 1. Now you might think that we need to reduce this, or that it's not in simplest form, because we got this is divisible by 2, 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 this is divisible by 2. So isn't there a simpler form of this equation that we could use that's still balanced? And unfortunately, that's not the case, because this coefficient of 1 on the phosphorus, if one of these is 1, then this is the simplest ratio we can get, okay? Because we have to look at the whole ratio of all of these coefficients, not just a few of them or some of them taken at a time. So 2 to 6 to 10 to 6 to 10 to 1, well, 1 is not divisible by 2. And so even though I could reduce all of these, if these were the only coefficients I have, because I have this coefficient of 1, that is as simple as this ratio is actually going to be. So this is the simplified form. Okay, let's double check it to make sure that we counted right. So if I have 2 calcium times 3 calcium, that's 6 calcium. I have 2 phosphorus times 2, so 4 phosphorus. There's 8 oxygen times 2 is 16, plus 6 times 2, which is 12. 16 plus 12 is 28. I have 6 silicon. I have 10 carbon. Now will these match? 6 calcium, 4 phosphorus from this 1 phosphorus molecule, 10 oxygen from here, and 18 oxygen from here, so that's 28, 6 silicon, and 10 carbon from the 10 carbon monoxide. So indeed, we've balanced the equation. This one is a little bit more difficult than some of the other ones we've looked at, but it gives you a good idea of how this can work. Now, would you have to do it exactly this way? No. If you followed some other order for multiplying your coefficients and changing those, you would still end up getting to this answer. Again, the tricky part about this one is mostly in that, you know, some of these elements, some of these compounds contain certain elements, and others do not, and you have to sort of achieve balance between the ones that have elements in common, like the oxygen here and here, or the calcium here and here, and then you can sort of do the leftovers, okay, the ones where there's only like one compound on each side that has carbon, there's only one compound on each side that has phosphorus. Okay, again, if you have questions, be sure to let me know.